Have you ever actually stopped to think about how many numbers exist just between the number 1 and the number 2? I mean, it's not just 1.5 or 1.9. There are fractions, decimals, and literally infinitely tiny slivers of numbers stretching on forever. It's kind of mind-blowing when you really think about it. Well, let's dive right into this notebook and uncover how we can possibly chart the infinite number of fractions and decimals that live between any two numbers. Welcome to this explainer, where we're going to write out and totally master the mathematics of intervals.
So here's the thing. Since it is practically impossible to list out every single real number between 2 points, like you'd be writing for the rest of eternity and still not be done, we use a really clever concept called intervals. Think of intervals as a brilliant shortcut. They help us represent these massive, continuous subsets of real numbers without writing forever. As you'll see on the number line we're looking at, this beautifully visualizes these continuous ranges. It is absolutely going to become our best friend today.
Okay, here's our game plan for today. 1. Charting the infinite. 2. The bracket rules. 3. Does it belong? 4. Operations, specifically intersections and unions. 5. Working through examples. And finally, number 6, your final practice challenge. Let's get to it.
All right, section 1, charting the infinite. Subtitle, the real number line.
To actually start charting the infinite, we really need to understand the playground we're working on, right? We're talking about the set of all real numbers, which mathematicians simply call R. Check out how we write these special sets out. It brilliantly illustrates how we can just slice up the entire number line. We've got the positive real numbers, marked as R+, and those stretch all the way from 0 to positive infinity. Then we have the negative real numbers, R-, coming all the way from negative infinity right up to 0. And the big one, R itself, that's the whole shebang. Absolutely everything stretching from negative infinity to positive infinity. Moving right along to section 2, the bracket rules. Subtitle, bounded versus unbounded.
Now, what's really fascinating about this notation is the sort of language of brackets we use to define the strict edges of our intervals. Let's see a quick trick to memorize this instantly. Look at the brackets we've got drawn here. A closed bracket is literally hugging the number. It's pointing inwards. That means the number is included in our set. It is a solid, hard boundary. But an open bracket, it's turned away, pointing outwards. That means we go right up to the microscopic edge of that number, but we do not actually include the number itself. So just remember, closed means included, open means not included.
Now, when we're dealing with unbounded intervals, the ones that stretch on forever, there is an absolute non-negotiable rule you must memorize. Be careful here. Many students make a mistake in this step on exams by closing the bracket on infinity. But let's think about it logically for a second. Since infinity is in a specific, solid number you can actually reach and stop at, the bracket must always remain open. Look at this handwritten example. We've got a closed bracket on the 2, comma, infinity, and then an open bracket. Always, always leave infinity open. All right, section 3, does it belong? Subtitle, testing elements with the belongs and does not belong symbols. So we use that funky little curved E symbol to say a number belongs to an interval, and the exact same symbol with a slash right through it to say it does not belong. Remember our rule, if a bracket is closed, the number belongs, but if it's open, it does not. Let's actually put this into practice. This is a common exam question right here. Does the cube root of -8 belong to the interval from -8 included to -2 not included? I want you to take a moment, pause the explainer right now, grab a piece of scrap paper, simplify that tricky number, and try to solve this before I show you the written steps. Go ahead, give it a shot. Okay, how'd you do? Let's walk through the handwritten solution together. Step 1, we simplify the math. The cube root of -8 is exactly -2. Step 2, we look at our interval. What kind of bracket is sitting right next to the -2? Step 3, well, we can clearly see the bracket is pointing away from it. It's an open bracket. So the rule tells us that boundary is a strict wall. Therefore, for step 4, our final written answer is that -2 absolutely does not belong in the set. Awesome. Let's jump to section 4, operations, intersections, and unions. Subtitle, when intervals collide. Let's see how all this builds when we start smashing two different intervals together on the exact same number line. This is where the magic really happens. We have two main operations. First up, intersection, which is represented by that upside-down U symbol. Think of an intersection as the overlap, the exact real estate where the two sets share territory. They both have to exist there. Second, we have the union, represented by a regular right-sided up U symbol. The union is basically the ultimate team up. It takes every single element from the first set and combines it with every single element from the second set, creating one massive unified interval. We also have difference in complement to talk about. Difference, shown with a standard minus sign, is just taking away whatever the two intervals share. You basically start with the first set and kick out anything that also happens to live in the second set. And the complement, marked with a little apostrophe, is basically looking at the entire universe of numbers and asking, okay, what is everything else on the number line that sits completely outside of my specific interval? Here we go, Section 5, Working Through Examples. Subtitle, Step-by-Step Mastery. Okay, I need you to grab your digital notebooks because we are going to write out a full problem step-by-step together, exactly the way you'll need to write it out on your next test. Here is our problem. Set X is the closed interval from -3 to 3. Set Y is the interval from closed -1 to open 5. We need to find the union of X and Y and the intersection of X and Y. Once again, let's be active learners here. Hit pause, sketch out a number line, and see if you can figure out the union and the intersection of these two sets before we solve it together. All right, let's look at how we visually solve this. The very first step you should always take, and I mean always, is drawing the number line. When you sketch this out, make sure to use solid, colored-in dots for those closed brackets and empty, open circles for the open brackets. Stacking the lines slightly above each other, just like we're drawing here, is a total game changer. It allows you to perfectly visualize exactly where these two sets overlap and exactly where they extend. Let's write out the steps for finding the union. Remember, union is that big, massive team up. Step 1. What is the absolute smallest point on our entire drawing? Well, that's -3. Step 2. What is the absolute largest point? +5. Step 3. We check our original brackets. It was a closed bracket at -3, and it was an open bracket at +5. So the crucial takeaway here is that our union stretches from the very minimum to the very maximum, giving us a final written set of closed bracket -3, 5, open bracket. Now, let's tackle the intersection. Here, we only care about the shared territory. Step 1, look closely at your drawing and find the exact spot where both lines exist stacked right on top of each other. Step 2, we can see this overlap begins at -1, and since -1 is solid in both of our sets, our bracket is closed. Step 3, the overlap ends at +3. And again, it's a solid dot in both sets, so it's closed. Step 4, our final written answer is the closed interval from -1 to +3. Notice how we meticulously check those inner boundaries to perfectly write out our overlapping intersection. And finally, Section 6, your final practice challenge. Subtitle, Test Your New Skills. You have done a truly fantastic job following along and learning these foundational rules today. But as any good teacher will tell you, watching someone else do math is very, very different from doing it yourself. To actually master this, you need to prove it on your own paper. So I am leaving this final homework challenge right here on the screen for you. Set X goes from closed -4 to open 2. Set Y goes from closed 0 to closed 5. Take absolutely everything we just learned today about open brackets, closed brackets, unions, and intersections, draw out that number line for yourself, and ask yourself, can you successfully chart the infinite on your own? Give it a try, have fun with it, and keep exploring.